All right, in Chapter 5, we're going to talk about regression. A regression line, we are only going to talk here about linear regression. So we're going to talk about a straight line that describes how a response variable changes as the explanatory variable changes. And we could use this line to predict values. There could be any number of types of regression. So when we were making our scatter plots, some of them were curved. We could find a line that would fit that curve and describe the pattern. We are only going to talk about linear regression, so just straight line patterns. So what we'll have is some sort of a scatter plot. Okay, so I got my scatter plot here. Does this have positive or negative correlation? Negative correlation. Is it a strong or a weak relationship?
Strong, weak.
I say medium-ish. There's a definite pattern to it, but it's not really tight together. But it's also not just like a wide open scatter anywhere kind of a thing. So what a regression line does is it comes in and tries to describe this relationship and kind of following through, in general, the middle of it. So one thing with regression lines that we should be able to do is kind of see a scatter plot and kind of eyeball in where is the general trend of this data and kind of plot that into the middle of it. That is a serious approximation, but that's the general idea. Then what we could do is use this line to predict for values that we don't have. So let's say I don't have any information about this particular x value. I could use the line to predict what the y value would be on that. It's not necessarily going to match up with reality because all of the points in this picture don't actually match up with that prediction line, but it would allow us to at least have a prediction.
Wait, sorry, what did you just say? I'm sorry.
So we have some x values of these points. So each of these points has an x value and y value. So some x values are covered, but not every single possible x value. So we could pick an x value and use that line to predict what kind of an output of a y value we would get. It won't necessarily be true then if I would actually take that measurement because all the points aren't going to be perfectly on that line. But it gives us a prediction. So in Algebra 1 and Algebra 2, we talk about straight lines and linear equations. And we use the equation y equals mx plus b. We're going to use that equation here, except in statistics, we switch the letters around just to be confusing. I don't know why. Y equals a plus bx is the general form of what we say for statistics. It's still mx plus b, but for some reason, we just move things around when we talk about statistics. This is our y-intercept, and this is our slope.
B? Right.
Yeah. When we talk about y equals mx plus b, b is actually the intercept and m is the slope. So here we mix around the letters and it seems a little bit confusing. But the coefficient of the x is the slope, and the number that's being added there would be our y-intercept. So in this particular picture, our y-intercept up here, if we bring this line all the way up here, that y-intercept would be our a value. And our slope is our rise over run, and that would be our b value. What can you tell me about the b value of this graph? I mean, you can't tell me exactly what it is, but what can you tell me about the b value or the slope of this graph? It's negative. Yeah. If we have a negative correlation, we'll also have a negative slope. We are going to be concerned with what is called a least squares regression line. And what the least squares regression line does is it takes every point and says how far is it away from what our line predicts it to be. So we take each point and connect it with a perfectly straight line and say how far is each of these points away from what the line predicts and says it should be, then we would take each of those distances and square them. That's why it's called least squares, and we're trying to make that as small as possible. That's the goal of what a least squares regression does. You won't need to do all that by hand. That would be ridiculous. To find all of those distances, square them, add them all up, and then minimize it, which isn't really a skill that you have for how to find a minimum. That's more of a calculus skill. So, but that's what the least squares regression line does, is it takes all of those distances of how far is the prediction line away from the actual point, take those distances, square them, and try to make that number as small as we possibly can. The reason, one of the reasons why we're squaring it is because when we square, it won't matter whether the point was originally above or below the line, because when you square something, everything becomes positive. So that's one of the reasons why we square it.
You just find the distance and then you square it, and that's your answer.
Find the distances and square it, and add them all up for every single data point. And we're trying to make that value as small as possible. And that's what would help guide us to this line. The equation of the least squares regression is going to be like this: y equals ax plus b. But specifically, our b value is going to be equal to r times sy over sx. So r is our correlation coefficient. So we learned how to find those on our calculator the other day. So that r is going to be our correlation. And then what was s? Standard deviation. So we take the standard deviation of the y values, the standard deviation of the x values. Remember from algebra, a slope is a change in y over a change in x, right? So we're still doing here a slope of a y over an x. Okay, so we're doing standard deviation of y over standard deviation of x. Multiply that by our correlation coefficient, and that gives us what our slope value is going to be in our equation. I will have for you a sheet when you take your test that has that formula on it. It's given when you take the AP test, so I figured since some of you may be thinking about taking that test, we'll kind of give you the same cheat sheet that they get when they take it. So if you take it, you're familiar with that kind of cheat sheet, but it's got some formulas on here for you, and that's one of them is what the B value is. So, and the A value is y bar minus b x bar. So we have to find b first, because then we use that to find our A value. And what are those y bar and x bars? What is that symbol? The mean. Okay, so to find the slope, we use our standard deviations. To find our y-intercept, we use our means. So this least squares regression is based on the mean and the standard deviations of the individual x's and y's. So we would take the mean of our y values, the mean of our x values, put them in there. You'll also see a symbol that the book calls this equation with a little thing, hat. It's called a hat over the y, just a little pointy thing on top of the y. We call that y hat. And that means it's a prediction of a y. It's not necessarily going to be what we would actually find if we took measurements, but it's a prediction for the y. So when you see that little symbol, we read it hat, and it means that it's just a prediction. Okay. I want to show you how we could do this by hand. In general, we'll be using our technology to actually find this line, but I want to show you how we could find this line by hand.
And by lines, those are the black line there.
Mm-hmm.
Right, okay.
Yeah.
Not the like orange.
No, those were our distances away. But. All right, so I have some data in here. I don't remember what it's from, but from at some point I put data in here in both my L1 and L2, so I'm just going to use the data that's in here. So what we'd want to do, I didn't want to do that. Let's see, 3.3. Okay. Get out of there. Okay, so to find our least squares regression line, first thing I would want to do is, like, let's take a look at a scatter plot and see what this stuff even looks like. So I'm going to go into my stat plot. My first plot is on, and on is a scatter. And so I'm going to go zoom, and choice 9 down the list is the zoom stat. So that's what this data looks like. I don't remember what problem this data was from.
This is how you're doing it by hand?
This is how I would do it by hand. So what we would want to do is first find that b value, the slope. And the slope was the correlation. So we learned how to find correlation the other day. So we'd go over to stat, calculate linear regression, and find our correlation there is our R value. Now, this actually, right there at the top, gives us our answer too, for what our final answer of our least squares regression should be. So if you were ever doing this, I guess one way, if you're taking the AP test, what they could do would be give you information about the correlation and the standard deviation and the means without actually giving you the data. So then you would have to plug stuff into the formulas. So, because otherwise you would just find the regression on your calculator. That's the way we're going to do it, is find our regression on our calculator. So my regression, I'm going to say, is 0.56. So write that down. Then our b value requires us to have our regression and our standard deviations for each variable. So to find standard deviations, I'm going to go into stat, calculate, and we did one variable statistics. If I just hit enter here, it's only looking at L1 right now. So it's giving me my L1 information, which is the calculator assumes that your L1 is going to be your X. We get a standard deviation of 0.14, I'll say, and we're going to need our mean later, so I'll just write that down here. Our mean is 2.9. Then I need the same information about the other variable, which I have listed in L2. So what I'm going to do is go stat, over to calculate, one variable statistics, but before hitting enter, I'm going to hit second and then number 2 and tell it that I want it to look at my second list instead of looking at my first list. It will default to always look at your first list, but you can tell it that you want it to do other ones instead. And then I'll hit enter and get this information about y. So y standard deviation is 0.32, and y bar, even though it says x bar, it's really talking about y, is 3.3. Okay, so then our rule is that b is equal to r times standard deviation of y over standard deviation of x. So on the calculator, I could do b, which was 0.56, 0.56 times the standard deviation of y, which was 0.32, divided by the standard deviation of x, which is 0.14, and hit enter. That will be our b value. That's our slope. So I get 1.28. That was my slope for this thing. Then our second rule was that a, or our y-intercept, is y bar minus b x bar. So then I got that information as well off the calculator, so I can do the y bar was 3.3 minus b, I just found out, is 1.28 times x bar is 2.9. Enter. And that gives me my a value is negative 0.412. So my equation would then be y hat equals negative 0.412 plus 1.28x. And I can confirm that by actually just letting the calculator do it. And this is how we're going to do it in our homework. Stat calc, linear regression, choice 4. and we get that same answer given some rounding error.
Wait, so it's a step back, but
Maybe
X
you
and
pull
Y,
back.
how did you get those S and X, like X and Y? There's two L's.
Yep, so X is your L1 and Y is your L2. So I had two lists of data done. So I did that by doing my one variable statistics. But if you just hit one variable statistics and hit enter, it'll give you your L1 data information. But the second time I did it, I made it do the L2 information.
So why did you do the scatter plot?
Just to see what the general shape of the data is. It is always a good idea to graph data before you do any numerical information on it. Because if I graph the data and I see a strong curve on this thing, describing a straight line for it just wouldn't even make sense. So it's always a good idea to see what your data looks like before you start doing any calculations on it. Okay? So this is how we're going to find our linear regression equations on our calculator. So same way we found the correlation coefficients for the last assignment, we go into that linear regression. The R gives us our correlation there, and then we get our equation with the A and B values. And just to throw things off even more, the calculator puts its A and B in a different position than what our book does. Why would it do the same thing, right?
So one more question.
Mhm.
Line over the Y thing. What is that? What's the difference between that and normal Y?
When it has the little pointy thing on top,
No, the next one up, the bar.
the bar, that's our average. When we put a bar on top of a letter, that means it's the average or the mean for that variable. Yeah. The little pointy thing is, we call it the hat, and that means it's a prediction. It's not necessarily going to be the true outcome. It is really only safe to predict close to the data you have. That's called interpolation, that we're finding we're just kind of maybe missing a piece of data, but it's within the range of the rest of our data. When we find something that is far outside of what our data is doing, that's called extrapolation, and that's dangerous because patterns can change. So just because a pattern is really strong for right now, that doesn't mean the pattern would continue on. So we can use a linear regression to predict as long as we're staying reasonably close to where our data is actually talking about. The last thing for today is to talk about some facts about this least squares line. So when we talked about correlation, we had some facts about that. We need some facts about this least squares line. The first fact is that explanatory and response variables matter. So with our correlation, we said it didn't. It didn't matter which one you put in as your X and which one you put in as your Y, you'd get the same correlation answer either way. Because this is describing the line of the graph, what's on your x-axis and what's on your y-axis actually matters, because otherwise your graph would be sideways, and that would give us a different line of an equation. So to get the right answer here, we really have to make sure that we're choosing the right thing to be our explanatory and our response. In general, to make that decision, I think about the idea of an explanatory variable as something that I have more control over. So if I was like running an experiment, what would I maybe be changing? And that's going to be my explanatory variable. And the response is what's being affected by the changes that I'm making. Okay? So you have to pick the variables correctly to be able to get the correct regression line. Correlation, it doesn't matter.
Wait, did you say which ones are going to be for like explanatory and response?
In general, if I'm trying to decide between which one's explanatory and which one's response, my explanatory is in general going to be, I think about if I was running an experiment, which one of these would I be controlling?
Oh, okay.
And
I thought
changing.
maybe for some reason you're talking about like X is always going to be
Oh, X will always be explanatory, and Y will always be response.
Oh, right.
But sometimes it won't give you like an X and a Y in your data. It'll give you a time and a distance, and you have to think about which one you're controlling.
That makes sense,
The second fact about correlation is that there is a strong relationship between correlation and regression slope. And that's because that formula we already looked at, that regression slope is equal to the correlation times standard deviation of x over standard deviation of y. So that correlation plays into finding our slope. If your standard deviations are always positive, okay? Always positive. Standard deviations are always positive. So that means that fraction part of this is going to be positive. So if our regression is negative, our slope will be negative. If our regression is positive, our slope will be positive. So that that correlation coefficient has a big effect on what our slope is going to be. The third fact is that our regression line always passes through the point x bar, y bar on the graph. So if you find the average of your x data and the average of your y data, the regression line will go through that point for sure. Okay, so that average point will always be a point on our regression line.
Average point will always be part of our regression line.
Yep. The point that's the average of each of the variables will always be a point on the regression line. And the last fact talks about this r squared value. So when we ran our linear regression, it gave us the two values that we needed to write our regression line. It also gave us our r value, our correlation, and it gave us an r squared, and we hadn't worried about that yet. R squared is the square of r. Okay, so it's really named well. It just takes the r value and it squares it. What it tells us, the fraction or percent of variation explained by regression. Okay, and we'll look at an example that makes that more clear, hopefully. This is just some information from example 4 in your book, but I wrote it up here as well. So we've got our R value of negative 0.7786. What does that mean about this particular data? What can our R value tell us about it? Okay, yeah, it's had a negative correlation to it. And what else? Strong or weak?
No, I think it's stronger.
It's stronger. Remember, closer to 1 and negative 1? 1 and negative 1 is perfect. Everything's in a line. As we get closer to 0, it's just a totally random scatter. So this is closer to a 1 or negative 1 than it is to being a 0. So it's definitely on the stronger end of things. Okay. So then we take that R value and we square it, and it becomes 0.6062. What this means is it says about 61% of the variation in this data is accounted for by the linear relationship. The other 39% is not explained by this relationship. So that tells us in a way how good of a predictor this line is. So if we're using our line to predict things, this prediction line is really only about 61% accurate. So 61% can be accounted for by this line, but the other 39% is something else going on. Okay? So that tells us how good of a predictor this line is going to be. The closer that our squared value gets to 1, the better of a predictor. Because if it was 1, then it would be 100% of the information is predicted by this line. So you could plug in anything and know for sure what the outcome would be. Okay? All right, that is the end of this lesson. So that is lesson number 9 homework.